Hi, everybody. Welcome. We're going to begin this session in just about 1 minute. Hi, everybody. Thank you for joining us. My name is Dana Carr, and I'm a member of OSA Management, and I'll be your room monitor for this session. If at any time you need assistance, please use the chat feature to grab my attention. Just before we get started, I have a few housekeeping notes. Please type any questions you may have into the Q&A pop-up box. If you see a question in the queue that you also want answered, you can click the upvote button to move it up in priority. The chat box may be utilized by the panelists to communicate additional questions. The webinar room will close at the end of the session. Please use the Zoom links on the schedule section of the NSF workshop page to join each session. Lastly, NSF will be sending a survey to you in a few days. We truly value your feedback and appreciate you being here. I will now pass this to our presider, Josh Combs, to start the session.
Hi, everyone. My name is Josh Coombs, and I'm an assistant professor at CU Boulder, and I'm chairing the session. And the topic for this session is quantum engineering in practice. So what is it like to be an engineer, the kind of skills you need, and so forth. So we have three panelists. Blake Johnson, who is a lead at IBM and was formerly the Vice President of Quantum Engineering at Rigetti. He's going to start off, and then I'll introduce the other speakers as we go. Please type any questions in. We'll probably ask some questions at the standard questions at the start of the panel, and then we'll move on to audience questions. All right, Blake, can you share your slides?
Yeah. All right, can you all see that?
Yes.
All right, then I'll get started. So I wanted to talk to you all today about the various forms of quantum engineering in industry. I have to start off with some caveats, right? That I'm not a researcher that studies the specific topic of how quantum engineering surfaces in industry. So the best I can do today is kind of tell you a personal narrative about my experiences working in quantum computing over the last 15 to 20 years in various different companies. I've started out in academia at Yale for my physics PhD, working with Rob Shulkoff, and then moved on to a defense contractor experience at Raytheon BBN, followed by a mid-size startup at Rigetti, where, as Josh pointed out, I was eventually the chief quantum engineer. So not only I should know something about this topic of quantum engineering, although I said to Josh as we were talking about this session today that I still am confused about what the boundaries are of what is quantum engineering, which is, I think, part of the difficulty in describing or defining a curriculum for quantum engineering is that I think it looks rather different from the perspectives of practitioners in these different contexts. And finally, now I'm at IBM, a large computer company. So, like I said, I'm going to tell you sort of my personal narrative to these places to try to give you a flavor of what quantum engineering was like and how it differed at these different institutions. I'm hoping that perhaps in the panel discussion towards the end, we can make some progress on whether what I'm describing here is unique to these places or whether we can pull apart some broader themes or trends. So, but just to start, where the story starts is sort of the academic experience. So, like I said, I did my physics PhD in a group in Rob Shulkoff's group studying superconducting qubits. And I guess here is where I was really first introduced to kind of an R&D cycle right? Where you go from modeling, you have some proposed experiment, you model it theoretically, and eventually you need to model the apparatus or device that you intend to build to test that. And then you go through actually having to design the specific apparatus and device that you're going to use to test it. You're going to have to make it, you have to fabricate it. Then you actually have the test itself, and then the analysis phase, where you usually will end up producing some paper or report. And particularly with the way that I experienced it in my PhD program, right, the grad students learn this entire cycle. And that's particularly well suited to training students to go off and start other academic careers where when they start their own group, they will be responsible for the whole cycle. But there's different specific skills that I learned for different parts of the cycle. Like detailed knowledge about qubits control, gates, and readout. It was particularly relevant in the context of quantum circuits to understand circuit quantization and how that's connected to the model parameters that you'd find in EDA tools for doing EM simulation of a circuit. Of course, there's nanofabrication methods, cryogenic and vacuum systems. This is somewhat dependent on the modality of the practitioner. Right, vacuum systems appear, and particularly ultra high vacuum systems appear in even the atomic qubits. But even cryogenic setups are not just for superconducting qubits, but also get used for dots and increasingly in ion traps for surface trap technologies. We learned sort of the rudiments of microwave engineering, in particular microwave transceivers, because we had to control and read out microwave pulses. Of course, other modalities might be more relevant to learn optics, but digital signal processing, I think, is something that's rather generic in all flavors of quantum computing and also quantum sensing. And of course, for something that's really trying to be a quantum computer, you have to learn about quantum channels and processes and how you verify or measure the closeness of a real world channel to an idealized one. So as kind of a gross picture of the R&D cycle as I experienced it in academia, when I moved on to Raytheon BBN, so I'm not sure how much of the audience today is familiar with BBN Technologies, but it's a wholly owned subsidiary of Raytheon. It was bought by Raytheon in 2010, but it's a company that's been around since World War II. And it's an R&D organization that is basically solely focused on government grants and contracts. And that funding model has some interesting consequences. I mean, the institution ends up being, it's industrial, but it's kind of quasi-academic because a lot of the work of working for a place like BBN involves grant writing or proposal writing. So the experience in some ways is not terribly different from what you would see as a junior faculty member at a university. You have to win contracts to support the work and the staff that you want to hire to work on those projects. But unlike the university, the staff that you hire are typically, there are other PhDs or master's students. And so they're more expensive than your typical grad student, right? So you have this government funding source, expensive staff, usually large overheads because of administering grants and contracts is non-trivial. And so that really forces small team sizes. And that has a consequence that, particularly at a place like BBN, that the people working on those projects still are responsible for that entire development cycle, right? So, we still had, an electron beam evaporator sitting next to a dilution refrigerator in the lab at BBN, for instance. But one thing that was new is because we're at a place that worked on a very wide variety of contracts, is that there was an opportunity for cross-pollination with other engineers. And particularly Raytheon BBN had a lot of people interested in and with expertise in radar and sensor systems, with FPGA electronics. And BBN has a rich history in sort of network and computer architecture, having participated in the development of ARPANET and initial email protocols and so on. And so there was a lot of interesting opportunities for conversation, and in some ways, getting some of those experts to work on quantum-related activities to bring their expertise to bear. When I transitioned to working at Reilly in the startup environment, the environment was extremely different in terms of how the company was built. So despite being a startup, it was actually much larger in terms of the effort that was deployed towards building quantum systems. And that allowed for a very different strategy for organizing the workforce. So instead of these individuals that were really responsible for everything, you now instead had a much more specialized workforce. So we had discrete domains of people that were really focused on just fabrication, just device design, just control systems, just RF engineering, and so on. And a lot of the people that we hired and employed in those disciplines, came out of a software engineering degree, or a software or a electrical engineering degree. And so we were training them or working together to try to find common language to talk to each other and understand each other. This is also the first time I encountered a new specialty of system deployment, right? So Reilly was trying to make available prototypical quantum computers over the internet. And so we had to, it wasn't sufficient to just have a laboratory experiment that worked once so you could collect the data that you needed for your paper. It really had to work whenever someone wanted to access it. And so this new specialty, which we considered part of quantum engineering for sure, had a rather different character than what you might think of in terms of typical development or research context, right? I mean, these employees really focused on system stability, efficiency, and robustness of calibration. And they had to have a lot of software experience in order to sort of handle a constantly evolving software stack and be able to ask questions like, we changed the way that that we write down calibration information, and be able to ask questions about, like, did that change anything about the effective process fidelities of the gates that are implemented on the stack. There's also a lot more contact with kind of traditional engineering skill sets, things like root cause analysis. Formal specifications became a big part of the job. Was to kind of manage this specialization into discrete disciplines. We had to sort of manage the interfaces and agree upon what we were building in these separate teams. And so a lot of the work in quantum engineering then became the learning how to translate, physically motivated specifications, like it has a gate error of 10 to the minus 3, or it supports measurement errors of 10 to the minus 2, convert those physically relevant metrics into the underlying engineering specs with an error budget that would add up to meeting those physical requirements. Another thing that was new at Reilly is there was an attempt made, at least, to try to train employees to work in the quantum engineering discipline coming from bachelor's degree programs, and particularly bachelor's degree programs that were not specifically physics, right? And so that was something called the Junior Quantum Engineer Program. And what it involved was a weekly lecture series, kind of mentorship or pairing with experts in those disciplines, and kind of culminating in a capstone project after 1 year, where someone was said to graduate from the Junior Quantum Engineer Program. And this program, I don't think there was anything like it when Reilly started it, but it had mixed success in the sense that most of the participants in this JQE program transitioned, rather than like staying with the company and continuing to work as quantum engineers in industry, transitioned into grad school because they decided that what they really wanted was a physics PhD or a computer science degree, for instance. And so it wasn't successful in terms of meeting the need of staffing the company. In my latest role now at IBM, it is somewhere kind of a mixture or hybrid between what I experienced at the startup and as a defense contractor, in the sense that you do see specialized roles, particularly around the development activity of scaling and deploying quantum systems. But there is a larger fraction of the workforce that is still dedicated to research activities. And that those individuals, we tend to hire people with the broad experience that you might find in the academic world with academic training. So you can have a mixture of the two ways of working that coexist. And one of the things that's also interesting about IBM is that the quantum team operates a bit like a startup in the large company, right? IBM is a massive company, but we're still a small quantum team in a way. But we take advantage of and draw upon the existing expertise throughout the organization for experts in nanofabrication, in packaging. Of course, IBM has a rich history in processor development and design for like the power processors architectures and the Z processors. And so there's been interesting opportunities to interface and engage electrical engineers coming with those that processor development background and integrate them into our efforts. But what I'd say is most unique about IBM compared to these other places, my other experiences at Rigetti and at Raytheon, was this effort to train and educate a quantum community was a much larger part of the activity. So I put together a slide that sort of gives you an overview of the different threads of this education activity. And there's kind of 4 pieces to it. There's a substantial internship and fellowship program sponsoring grad students and postdocs even at universities, and often getting those grad students to spend time with us at IBM working on our research projects. We have Qiskit camps. So Qiskit is IBM's open source quantum software framework in Python, and the Qiskit team runs these camps around the world. We're of course kind of on pause with that activity because of COVID, but where people can get initial exposure to Qiskit. And one of the fun things is that's happened in the past few years is the initial camps had a focus which was, I would say, purely recreational in a sense. Like there was a lot of activity in quantum games. But in the last year and a half of these camps, while they were still running, we started to get more and more people coming that wanted to do little research projects. And so, you'd have people making little new programming interfaces. They'd be looking into verification and validation schemes, optimal control. And so there's really starting to engage with a research audience too, even in those Qiskit camps. There's a YouTube video series for trying to lower the barrier to entry to get it started. And perhaps most relevant to this audience today is our efforts to build an open source textbook. So the Qiskit textbook, which you can find on qiskit.org/textbook, really tries to offer, I mean, it's meant to be a supplement to a university curriculum, but it tries to offer kind of an alternative path to what you might typically find in university. In the sense that rather than starting with sort of the mathematics of quantum mechanics, it really starts with a programming first perspective, which may be a better or an easier path for us, someone with a software engineering focus to get engaged in quantum computing. So this is, like I said, it's an open source activity, so others are free to contribute to it. And already we're starting to see some classes start to integrate this material into the day-to-day activities in universities. And so I'm excited to see what happens with this and where it goes. So just to wrap up, again, this was my kind of personal narrative of working at 3 rather different flavors of industrial quantum computing companies. And again, I hope to discuss with the panelists what aspects of these are familiar to them and which ones are different. But if I take my own stab at pulling out some similarities and differences, things which are common is that communication skills seem to be relevant and necessary in all environments, whether it's grant writing or presentations and reporting or papers. No matter what, you need detailed knowledge of control, quantum control, gates, readout. But what really ends up being part of the day-to-day is interfacing with other kinds of engineers, people with other backgrounds and training, and learning to speak the language of engineering as opposed to just the language of physics. But some of the differences are that some of these environments require sort of broad expertise, like what you would typically find in an academic PhD program, whereas others allow for their models are built around greater degrees of specialization. So what we mean by quantum engineering, I think for me at least, seems to be very context dependent at these different kinds of places. So with that, I think that wraps up my comments for today.
Great, thanks, Blake. That was a really stimulating talk. And I think we'll just hold questions as we said at the start. And if the audience members have questions, please type them into the Q&A box and or into the chat, and we'll table them for a bit later. So next, I'd like to introduce David Reilly, who's a professor in physics at the University of Sydney in Australia. And he also is the a principal researcher and director of Microsoft's arm in Australia. And he is one of the few experimental physicists that I know who is seriously undertaking a quantum engineering effort. So I'm very curious to see what he has to say. So David, if you're there, can you share your slides?
Sure, thanks, Josh. Let me share my desktop here. That work okay?
I can see you and I can see your slides, so you're good to go.
Perfect. Great. So look, thanks so much for putting together this this workshop. I'm pretty passionate about this topic because it's my daily life, is trying to understand how to, create an environment where people can get on with their job. And the interface between engineering, physics, and many of these other disciplines is actually really challenging. And, I think it's an area where we have a lot of work to do to be able to educate people, train people in the foundations, but also understanding how the interface between these different disciplines is meant to work, because that's what quantum computing really, requires. So it's a struggle for me. I was thinking even, in the last sort of 24 hours, the number of interactions I've had, which you can kind of trace to a root cause challenge that has to do with the multidisciplinary aspect of quantum computing, and also the different philosophies that underpin how engineers think compared to, for instance, physicists or those from a research background. And I think that challenge is something that could be improved by having a series of programs, both at the undergraduate level or at the graduate level, that from the beginning starts to really kind of tease out these challenging interface ideas and trains people in an understanding of what those disconnects look like and how to kind of walk around them. And I think that would have broad impact, not just in quantum computing, but probably in many other disciplines actually as well. So I'm not sure if people are familiar with this nice article in New York Times that came out a year or so ago. Some great quotes here. Shortage of researchers in quantum computing, and I really like this quote from Steve Gervin, that there really isn't many people at all. There could be less than 1,000 people on the planet that understand quantum computing sufficiently to be able to educate the next generation. So we're really bottlenecked in this field, I think, by people that understand the details. And what I want to really point out is that it's not just an understanding of quantum mechanics, but it's also an ability to be able to bridge quantum mechanics with many other disciplines. As Josh mentioned, I have a role in Microsoft. I work for Microsoft. I also have a position in academia at the University of Sydney. And my position reflects Microsoft's kind of perspective on this challenge. Across the world, our program is distributed in universities as well as in industry centers, obviously in the US, in Redmond, in Seattle. And the reason for embedding in academia is because recognizing that quantum computing is still at a stage where we need both research, fundamental physics, but still also need that industry mindset and the kind of muscle of industry to be able to actually deliver on some of these technical challenges. But I think if it's over to academia entirely, then we get wrapped up in obviously the metrics and drivers of academia. Where's the next publication? Obviously professors think very much like that in terms of grants, publications, academic promotions, shorter time scale in terms of the technical activity. If it was all over to industry, I think we equally wouldn't succeed. There's still a lot of research to do here, very fundamental physics, a lot of concepts that are not traditionally taught in engineering schools, and very few people, actually, to be honest, that have come from an entire industry background that find themselves in a position to be able to understand this stuff. So looking at the broad different technologies that we envisage at the moment related to quantum mechanics, I mean, spanning from computing through to communications, sensing and imaging, and so on. All of these different domains are pretty broad. I mean, they touch many different fields. Of course, underneath it all, there are unique quantum phenomena that we're really kind of tapping in order to realize some new technology. And as you look across these sort of three key areas or three key pieces of physics that underpins much of quantum technology, it's interesting to just think about to what extent is what I've even got on the screen there, even these broad concepts, intelligible to graduates from typical engineering degrees. And I think the answer is hardly at all. These are foreign concepts, and yet they are the underpinning fundamental phenomena that is at the core of quantum technologies. So just to wrap up, I mean, I really think that a quantum engineer is a bridge. It's a person who has familiarity with engineering practice, and as Blake said, this is actually quite a very different perspective on how to understand or how to make progress on something. Frequent activities, design of experiments, DOEs, looking for correlations. If I change this variable, this other variable will change. I don't care what these variables are or what their underpinning mechanism is. I just want to be able to optimize a problem. So failure analysis, very important. Specifications, very important, and processes that really look for correlations. And I'll, on the panel, in answering some of those questions, want to give you a particular example and story of a recent, I'll call it an incident that I experienced in relation to the disconnects that can exist in that space. On the other side of the bridge, of course, research methodology. Physicists and scientists are driven to understand fundamental mechanisms beyond just correlations. And I think many of those mechanisms have an underpinning in quantum concepts. And so the quantum engineer, familiar with both of these worlds, I think acts as a translator and a bridge and a means of pulling the best out of both of these approaches and constantly connecting them, almost on a daily basis. And there are very few people that can, at the moment, act as a bridge between these different domains. So to me, it's not really about the specific skills on either side. It's really about this sort of broad attribute that you would want to have in graduates that from the get-go, baked into their whole training and their education is an understanding of these different domains, how they relate to each other, how they potentially disconnect from each other, and their role in acting as a bridge between those two domains. And with that, I'll hand over. Thanks.
Great, thanks, David. That's really interesting. I hadn't I guess you and Blake have both sort of emphasized this systems engineering. So maybe we can delve a little bit more into that in the panel.
Yeah, absolutely. Thanks.
Yeah. All right, thanks for that. Jeff, are you there?
Yeah, I'm here.
Great. Maybe you can start sharing your slides. And so
start sharing my slides.
Yeah, so it's fantastic to have Jeffrey Shapiro here. He's a professor at MIT, And MIT has this great history of quantum engineers, including people like Herman House and Jeff and Will Oliver and Dirk England. So I think it's really one of the programs around the world that we should be looking to for guidance in quantum engineering. Take it away, Jeff.
All right, thanks, Josh. I'm glad to be invited to participate in this workshop. Very interesting so far. I'm going to take us in a bit of a different direction. We've heard a great deal about quantum computing, and of course that's extremely important. But I'm going to talk about quantum communication, which is the field in which I've worked for many years. And communication, to me, in this context, includes transmission of classical information, transmission of quantum information, quantum key distribution, and other techniques for quantum secured communication, quantum imaging, quantum radar, quantum interconnects between different quantum devices, and quantum networking, although I've really done very little, if any, on the latter. So let me begin here. From my perspective, coming really from academia, pretty much exclusively, except for interacting with Lincoln Laboratory and BBN and some other places. It seems to me so far, quantum engineering as such is primarily the work of doctoral students and postdocs, professors, technical staff at the PhD level. And that's not going to be enough personnel to build a real quantum ecosystem. We're going to need quantum engineering workforce with large pools of what I prefer to call quantum aware bachelor's and master's engineers. And to me, that means they have degrees in relevant existing disciplines, but their programs, whether they have formal certificates or minors associated with them, incorporate quantum into key existing subjects, and of course, supplemented by new subjects. And these quantum subjects are provided throughout the undergraduate years, and a broad menu of first-year graduate subjects also available to these students. So I'm going to be rather specific. I'm called up here the electrical engineering and computer science flowchart for the bachelor's degree of that title out of my department. And it starts at the very bottom after you've done some of your calculus and physics with differential equations and programming skills. But let me focus on these introduction courses. One of these has to do with an introduction to ECS through robotics, another one through medical technology, a third one through, I'm losing track now. One of these has to do with embedded systems, and there's yet another one, I can't even remember anymore. But they're all distinguished by having a significant amount of hands-on activity and really propelling you forward into the mainstream of the curriculum. And you can read this up through the foundation level subjects span traditional E, traditional CS, and things that sort of straddle in between, such as inference, which lends itself to the beginnings of machine learning. Then we have what we call header subjects, again, going deeper into all these various levels. And up at the top, advanced undergraduate subjects provide more specialization, and there's room for some electives. And this communication subject is not communication in the technical sense. This is a soft skill. This is oral communications. And then there are some specific constraints that go with this program. Everybody has to have an independent inquiry subject. That means something that teaches them, write a proposal, do the project, get a midterm review, get feedback, and progress to an endpoint. And it includes both hardware and software type activities, not in any one subject necessarily, but you don't have to do a hardware independent inquiry subject. Everybody's got to take, in addition to that, a department laboratory subject. Everybody's got to learn probability. And then there are these three things that I'll gloss over because there are a list of electrical engineering subjects, a list of computer science subjects, a list of undergraduate subjects in that middle sort of EE and CS-ish sort of area. And this is not necessarily an additional set of 6 subjects on top of what I showed you on the flowchart page. Many of the subjects in that list will check off parts of these lists. The idea being with these constraints is to ensure some significant breadth across the entire span of ECS. Now, to begin to incorporate, or perhaps even complete incorporating quantum into this, there are many places in which that can be accomplished. The first thing is, in addition to that 601, 602, 603, let's have a new introductory subject on quantum computing and communication. I should note that that introductory subject is taken typically first term sophomore year, but for students who come in with some advanced preparation, they may even take it the second semester of their freshman year. And so this new introductory subject would launch entering students into the quantum area at the outset of their major. And that will enable in some of our large subjects, undergraduate subjects that have lecture recitation format, to create quantum aware recitations. For example, in the undergraduate algorithms course, if you've taken the introductory subject on quantum computing, you could be in the recitation that taught you some about quantum algorithms instead of just ignoring that. We could have quantum independent inquiry subjects. We could have a quantum departmental laboratory subject, or maybe two different ones. And this particular program, at least at MIT, given the faculty we have and the other activities presently underway, we could initiate a program like this soon. The new introductory subject might take a while to develop and pilot, but many of the other things could be begun quite quickly. Now, I guess my last slide must be the next one. In the 1990s, my department felt that for many of our students, the bachelor's degree wasn't quite enough. Many of them were going on either on their own or with company sponsorship to get a master's degree. And so we felt, why not provide our undergraduates, many of whom are not planning to go on to doctoral study, the opportunity to stay on a year and a half more and complete an integrated master's. They get their bachelor's degree, but then they get a master's of engineering degree built on one of our undergraduate degrees. And here I'm going to say something about what would be built for one of these quantum communication engineers on the EECS baccalaureate. First of all, every MEng program has to have 2 restricted electives in mathematics from a short list, but also 4 graduate subjects, what we call it, approved advanced graduate subjects from a list. And out of the advanced undergraduate subjects, the AUSs they took in their undergraduate program, and these AGs, there has to be a 3-subject concentration. And of course, a master's thesis. And this flexibility allows quantum students who've come up through that quantum introductory subject, a quantum departmental laboratory, a quantum independent inquiry subject, and the quantum recitation sections of some of the undergraduate subjects. Along the way, these restricted electives are often taken by students aspiring to the Masters of Engineering while they're still undergraduates. So linear algebra and discrete mathematics, which are very important, I think, for quantum computation, quantum communication, are on the list of restricted electives. We could develop advanced undergraduate subjects in quantum engineering. We don't really have any now. We do have a host of AG subjects in quantum information science, quantum technology devices, quantum complexity theory, and so forth. And new subjects might well appear. And of course, a student doing an MEng thesis in one of the research laboratories doing quantum information science engineering will capstone the whole thing. And this program, I think, could be initiated soon, and probably could be initiated at other research universities that have similar sorts of programs. And although I focused on EECS because it's my department, it's what I know well, it is also the case that things like this might be developed in mechanical engineering and perhaps other departments too. And that's it for me.
Great, thanks, Jeff. That was fantastic to have that perspective. So if David and Blake can turn on their camera, we'll start the panel discussion. And we're going to start with some pre-prepared questions. And as questions are filing in from panelists in the audience, we'll add them into the mix. So please go ahead and enter your questions. So I wanted to maybe start with this point that Jeff made, which was, for the most part, we've been hearing about quantum engineers in the context of quantum computing, and many people in the audience haven't really experienced engineering outside of that context, or even within a quantum computing company, the kinds of engineers. So I'm just curious from the 3 panelists, what are the kinds of quantum engineers and how do they play together? I don't know who wants to have a start at that.
Well, I think that there are a great many things that go on in industry. I think from Blake, we've learned that in large companies, you're not going to cover the waterfront. Any one engineer will have to assume responsibility for some portion of the overall activity, but very importantly, interact with other disciplines. So I think that's going to be the case. I mean, it is absolutely clear that fiber optics are going to link these quantum processors, maybe over modest distances and certainly over longer distances. And therefore, somebody's going to be a photonics engineer. And photonic integrated circuits are going to make a big difference in this regard. And so there's going to be that kind of expertise, but somebody's got to do the interconnect to the microwave if the superconducting systems are ever going to be put on a quantum internet. And you have to think about what's required. And there's a lot of stuff going on, including a great deal of learning somebody else's language. Over the years, I've collaborated with people from a variety of areas, some in industry, some in other departments, some at other universities. And the first thing you have to do, and it's been mentioned earlier, is to learn to speak the other person's language and conversely.
Yeah, this was really interesting. I mean, I think you hit this phrase, was it a quantum aware engineer? And that was really something that both David and Blake hit on in their talk too, being able to sort of talk across these boundaries.
Yeah, I think Jeff is certainly onto something there with this concept of language. It's certainly I've learned over time to speak more comfortably in the terms that the engineers are comfortable with, whether it's loss, impedance, and so on, these kind of traditional kind of microwave engineering or electrical engineering terms, but also if you spend any time with people of a traditional engineering background and you want to do something new, you get used to the first question out of their mouth, which is, what are the requirements? And I remember as a physicist first encountering engineers, this question used to always frustrate me because it's like, well, the requirement is that the gate error is as low as I can make it, or that, the gate speed is as fast as it can be, or like the noise is as low as possible. And, they would very recently turn around and like, I can't design you a DAC with noise as low as possible. You got to tell me what the noise actually has to be, and then I can tell you what I can build. So there's a bit of kind of understanding both the words people use, but also kind of the practices or workflows that are kind of typical to their domain in order to understand how you're going to work together.
Yeah, I would just underscore what Blake said. It's actually really refreshing for me, again, given my day job, to hear Blake's perspective, because it's a struggle, and it's exactly right. Engineers, conversations, the first thing you hear is, what's the spec? Give me the spec. And the answer is, well, tell us what you can kind of hit, and then we'll figure out some way to use what's working well to do the thing that we want. And the spec's evolving, and we're trying to penetrate into that dense fog of new concepts and understanding. So language is key. Understanding the differences between the way in which engineering and scientific domains approach problem solving, I think, is also important, but really challenging to bring across on a day-to-day level.
Right. So I mean, one of the things it sounds like we need to train engineers to be quantum, but perhaps we also need to think about how do we train scientists and physicists to speak engineer as well. So
yeah, and I think recognizing that when you hear that other language and that other approach, to be able to realize, okay, I see how to kind of in my mind account for that perspective, see its value, and not immediately reject it. And that's often what happens is engineers just think, well, there is no spec. You guys, must be incompetent because you haven't even written down yet the blueprint and the spec. And that would be obviously the first place to start. And if you haven't done that, then you probably have no clue. And vice versa, you hear the opposite. So I think from, as I mentioned before, just having programs that build in an awareness of the differences and different approaches to solving problems and building things would be amazing.
All right, I might just ask one other question from this pre-prepared list before starting to mix in some of the audience questions. And it's one that I'm really interested in on getting engineers and people who work in industry's perspective. And this is, how do we go about training engineers? And there's like constraints on this because, no matter what degree you do, whether it's professional or not, there's a certain amount of subjects that you can set aside for any particular speciality, whether it's in electrical engineering, whether you're doing DSP or comms or control theory or RF, whatever it is. There's only so many subjects you can set aside for that. So given those constraints and the fact that engineers do on-the-job training, what should we, or how should we train theoretical engineers, or how, and more importantly, how do we go about training experimental engineers who might have to work on, for one job, atomic systems, and for another job, microwave and superconducting systems, or optical for that matter?
So I'm kind of happy to jump into that one first off. I'm a big supporter of actually, when it comes to formal education programs at undergraduate or graduate level, even, to have an emphasis and a focus on the attributes as opposed to the specific skills. I think the critical thing that I'm looking for in hiring people is, some evidence that they know how to think, and that they've been trained in how to think generally. The specific skills are important, but also map broadly from one discipline to another once you're acclimatized. If you know how to learn and you know how to think and you can work autonomously, and you have that critical thinking, attributes and skills, then a lot of the specific details and training is something that can be built up over time. If you don't have that initial ability to, figure things out for yourself, you haven't, really, I think, had experience in critical thinking and problem solving, then it's really challenging. And that's where, you get into this sort of situation where, it's kind of often spoon feeding people and giving them almost daily instruction as to what they should do. Even though they may be deeply skilled, they don't know what to do next. They don't know how to figure out whether it's relevant or not, what the prioritization is. And so I struggle a lot with those broader attributes. And I think that, degrees these days, which are packed full of lots of courses, so many broad skills that are, and specific skills that are needed. I think the foundation needs to be these sort of graduate attributes associated with critical thinking, problem solving, autonomy, and so on. And again, back to that bridging idea, an understanding of the differences between these domains and how one might use the best of both worlds to solve problems.
Right. And that seems consistent with, some of the things that Blake was saying in his talk about, there's even within industry, there's different kinds of industry, and the skills are different.
I think it's clear that David's quite correct about this. For one thing, be you educated as a scientist or as an engineer, unless you leave behind over the course of your career, either your science or your engineering, or if you were a mixture of both, you're going to be a lifelong learner. And so you have to have a certain fundamental grounding that comes out of your undergraduate education, which may be built upon in terms of hands-on experiences you had then and internships perhaps you had then. But you're never going to be the type of person who comes into a career with everything you could possibly need to know to fulfill that, not just that initial employment, but 20 years, 30 years worth. You have to be able to adapt to the changing technologies and maybe even contribute to the development of the new technologies.
Yeah, I would say I agree with David that particular skills are, you're more likely than not to miss what they need on the particular job that they end up into. But I think if you take a lot of, you can take any example that you might have find in an advanced undergraduate laboratory course, whether it's a pulsed NMR experiment or a simple tabletop optics experiment, to use it as not trying to train the specific skills that they'll need to do the work that they're going to do in industry. But more importantly, is like a test bed for figuring out what to do when things don't work, which is actually the most critical thing to actually being a good experimentalist. Is not how do I build a micro transceiver system, is how do I fix a broken one. And it doesn't have to be that specific broken one, but just anything that doesn't work, how to take it apart and think about it step by step, piece by piece, until you get it working again. And that's something which you can learn in a variety of contexts that is a transferable skill in many cases to other technologies. The other thing which I think is useful, which oftentimes we struggle to teach, is what sometimes is called a sort of a systems mindset, right? The ability to think not about how your particular component is functioning, but how it interacts with the ones around it. Because a lot of the times that we struggle with, or we notice the difference between people that have had like a PhD kind of training and people with just a bachelor's or undergraduate degree, is the kind of the pitfall of becoming trapped and thinking about just my component in isolation and not understanding how changes in one place can have consequences up and down the stack for good or for better or for worse, right? How maybe some small change here could actually make it possible to build design in an entirely different way that might be cheaper or easier.
Okay. So maybe we'll move on to one of the questions from the audience. So here, this one was in particular for Jeff. How common is it for physics or CS majors to pursue an MEng? Could the new quantum track become more attractive to those majors? Yeah, I don't know if you have thoughts on that.
In specific terms at MIT, the MEng is only available to our own undergraduate majors. However, the courses that I described could be taken by other majors. But we already have a double major baccalaureate with the physics department. And I've had, as registration advisees, a number of those students. So they take more physics than the typical electrical engineer, computer scientist would, and they could easily fit into this track. But for that matter, I think other universities could package this differently. But I think it would be easily possible to do some more physics and try to stay closer to the hardware side of things in going forward with these quantum courses within ECS, because they'll probably want to get some of the CS background. We also have a joint Bachelor of Science in Computer Science and Physics. I think we have that too. So there are a variety of things that are going on. There's a minor in computer science also. Oh, the computer science joint is with mathematics, which is another interesting place.
I see.
Which to have overlap at the theory side.
Kind of related to that, one of the questions in the chat was about the balance of the interaction between EE and CS as an engineering discipline, and how does that work at MIT, for example?
At MIT, we're a single department, whereas at many other schools, CS is a separate department. And the department is quite large, and the span of its teaching and research activities is enormous. So there are some areas in which there's lots of interaction between people who characterize themselves as computer scientists and people who characterize themselves as electrical engineer. And in the middle, in the areas of AI and machine learning and robotics, it gets blurry as to who's really considered EE by their own choice and who's considered CS. And of course, MIT has now established the Schwarzman College of Computing. The ECS department is jointly reporting to that dean and to the dean of engineering, and department is reorganizing itself in a variety of ways to pursue the important things for the future. And quantum computing, quantum engineering are both very much on our agenda.
Okay, and another question from the Q&A. So this is again, this nice term that you brought up, Jeff, about quantum aware engineers. And so the question is, what's the need for these quantum aware engineers who have sort of domain knowledge and, say in RF engineering, but also know enough quantum, and what's the sort of depth of knowledge that's needed in quantum in this context? And perhaps maybe because we're talking about education, how would you imagine this is delivered?
It is the case that there's going to be an enormous amount of classical engineering to build a quantum computer. And it is important, or for that matter, a quantum communication system. It is important, I think, for bachelor's, master's level engineers who will be involved in industry when we go from the point of everything being a PhD level research idea that has to get ultimately built into a prototype and tested to something that can be manufactured and undergo the cyclical redevelopment and improvement process to make a large scale market opportunity come to fruition. It's going to be much better if these master's engineers can speak enough of the language to realize what they need to achieve and make it easier to accomplish some of the translation Blake was talking about, that they're not going to demand, tell me the specifications. They can talk on par with with a physicist who's developed this new nonlinear optics to couple microwave to 1.55 micron, and understands some of the issues associated with building both the microwave side, if they're the RF engineer, or the optical side to mate it to optical fiber. And so I think that's going to be a very valuable and important thing. And over the course of someone's career, they could transition from this. Maybe they go on to a PhD later, or maybe they just move up the ladder and learn the physics. I mean, people of my generation who were involved in this kind of work didn't get taught any of it in classes. It wasn't available in classes. So we learned it on our own.
So I wonder, David and Blake, if you have perspectives from industry, like for example, like when someone who's not quantum comes in and starts working with you, how long does it take for them to get up to speed?
Yeah, let me tell you a story. This is a true story. Just to point out, the challenges here. My research group, when we were in sort of from academic background, had spent a number of years trying to develop electronics, CMOS electronics that works at deep cryogenic temperatures. And the way we went about solving that problem was, we understood the underlying physics, and we built a lot of models and process design kits for understanding the behavior of semiconductors at low temperature, and being able to design around that, and capture many of the phenomena that occur at low temperature, and made a lot of progress, doing that. And when I joined Microsoft, there was also a cryogenic CMOS activity. But at that time, there was little progress. And the first conversation I had with the engineers in the lab, they were cooling various devices and said, well, we're having a lot of trouble. It doesn't really seem to work. And I said, well, what technology node are you using, and what is the particular phenomena? And they said, oh, we basically just buy things from wherever we can get them, and we cool them. And the ones that work, we put in this bin, and the ones that don't work, we put in that bin. And we buy enough stuff. And I said, how many are in the working bin? And they said, at the moment, 0. So, but that was the approach. It was like, there must be a distribution of working and not working, and I can filter the distribution into things that work. And I don't need to understand anything about the underlying physics. Okay, so I sort of, had a lot to say about that particular approach and how I wouldn't really succeed. 6 months later, I had another conversation with this group, and I found out that they had spent 3 months trying to build a new numerical model from the ground up to calculate band structure of silicon. And they said, but you told us we need a fundamental understanding of what the underlying physics is. And it was like, yeah, but you can read it. You can look up the band gap of silicon, in 2 clicks. You don't need to build a numerical model and so it's really interesting, without being disparaging. It's just a total disconnect between the skills that they have and how to use those skills, when to start, when to stop. Like, do I need to know entanglement in order to measure the impedance, or can I just treat it like, when can I think this way, and when will that get me into trouble? And, I think, again, back to those sort of broad graduate attributes, it's a very hard thing to teach. Where does my knowledge fit? Where does my knowledge not fit? And, how do I sort of make sure that I'm actually working on something in an effective way? Really challenging, but I think it can be taught via examples and experience. And I think, degree programs that are structured with an awareness of those kinds of disconnects, I think would be extremely powerful for this field.
Using a story, David, I haven't experienced anything quite like it, but I have flavors of it too from my own history. I guess to Josh's question about like how long does it take to get an engineer up and running, I guess, in these large teams, typically when someone enters, right, they've already broken down what they're working on into lots of, of intermediate milestones and checkpoints and lots of tasks, right? So generally speaking, someone getting up and running, they can, in their second week on the job, start to do some activity that is productive and worthwhile, right? Because the problem has been translated for them already into their domain. Right, it's like build me an FPGA model that takes module that takes these inputs and converts them into that output, or build me a software function that takes this kind of data and presents it this other way. Right, so there's generally when someone's starting the conversion into their language has already happened by a more experienced member of the team, so that they can get going already. It's when the next project starts and they're trying to participate in sort of breaking down the tasks, the larger project to do its subtasks, that whether or not they've had any of the training starts to become relevant. Although, I mean, so I guess I would say for me, at least, like there's kind of a minimum set that everyone can benefit from, right? Regardless of which part of the discipline they're trying to attack, which is that if you're building a machine that has certain operations, whether it's for a communications task where you need to send and receive bits on a channel, or a quantum computing task where you need to do these operations on the device, like having some basic understanding of what those operations are, what their action is, so that you understand like what is the ultimate goal of the thing we're building, so that I can connect my work or the work of my team to making those things better. Like that's the minimum in order to sort of engage broadly with the outside of their own little sort of micro discipline.
Okay. So I guess while we're on the topic of training and education related things, there's a nice question to the panelists here about, how long would it take to take an engineer to, or how much quantum information do you need to know to wire a fridge? And can you just get an RF specialist off the sidewalk and train them to wire a fridge? So I think Blake has already responded to this in the chat, but I guess it would be nice for everyone to sort of hear the response, and maybe David has some thoughts on this too.
Yeah, I think I would lean towards a microwave engineer that knows how to translate that knowledge, knows how to kind of abstract away aspects and say, all right, I'm going to call that particular part of the circuit the load that I'm familiar with. Wiring a fridge, is a little bit more than just the microwave engineering, and that there's obviously an awareness of some underlying physics, black body radiation, thermal noise, and that kind of stuff as well, that a lot of microwave engineers already understand. So yeah, I would say it's not necessary to have a deep understanding of quantum mechanics to do that. It probably helps to have an awareness, but the appropriate amount of awareness. It's, you can go too far, and many example of students and professional engineers who, haven't yet sold an SMA connector because they thought they needed to understand quantum entanglement before they, actually commence that. And so it's that balance of realizing I don't need to know that in order to be able to accomplish this task, and other instances where, okay, I do need some level of awareness as to how this impacts the broader picture, and navigating that space, I think, is the hard part.
I'd like to jump in on this. I guess it's been irking me for a while during this workshop, and so I'll finally talk about it. I think there's a real distinction between training and education. We're preparing people in universities and other places with professional degrees in engineering, going to become quantum engineers or quantum aware engineers, preparing them for perhaps a career of 40 years, unless they move into a management chain or something else. Training, I don't know anything about wiring a dilution fridge, okay, but it strikes me it may be a very challenging hands-on task, okay, but you're training somebody to do that. And as long as we're stuck, and maybe we will be forever. I know nothing about dilution fridges, except when I was lab director, I found out how much they cost and what the cost of provisioning a room that could house one of them was. But in any case, hand wiring things is not something you do on a scale of everybody's got a dilution fridge in their house next to their IBM PC or their Mac. And I know very well, because I work in optics, what an optics table looks like for people like Akira Furusawa, who's done all these wonderful continuous variable entanglement experiments. That's never going to be anything other than a research laboratory or university laboratory thing. You've got to get it onto a chip, both for the robustness and the size. And the chip, well, you design a chip, you send it out, you get a fab, you test it, all those things in the research cycle, but then you come down to a manufacturable item, a reliable manufacturable item that can be part of a real system and function. And so we're going to need to have people, technicians of an appropriate quantum type, who can do the wiring of fridges and other tasks right now, and maybe ultimately they can be a machine that will wire one of these things up. If we need them in great volume, I think it's going to have to be that way. But there's going to be need for quantum technicians too. Technicians who will work on quantum stuff. They need to know what perhaps is important about it. They need to have at least a semi-quantitative but real qualitative understanding of what they're working on. But they have hands-on, very essential techniques for which you shouldn't need a PhD in order to do a great job.
Blake, this sounds like the things that you were mentioning in the chat. So I wonder if you could sort of re-explain some of those.
I mean, to Jeff's point, right? Like we have used technicians at the various places I've worked at to do things like fridge wiring. Jeff's exactly right that this is more of a training exercise than it is an education exercise. I mean, I will note that, you know, in practice, it is sufficient usually to like write down the diagram and train someone, you know, have them shadow some of the done before a few times and then have them do it themselves to check their work. So in that ways, it's no different from trying to teach someone how to do any other sort of hands-on physical skill. You know, it takes work and discipline to do it well, but like it's not necessarily you don't necessarily need coursework, formal coursework in order to master it. The thing which is which does come up though from time to time is those that are just sort of following the diagram are subject to you know, there is no chance that they'll get it right if the diagram is wrong. Right. And I can't tell you how many times the physicists like accidentally swapped the cables when sort of drawing the diagram. But when they walk over to the fridge to check it themselves before closing it up and cooling it down, that is like is blindingly obvious. Like, oh, that's the input is connected to the output, and then they check their own diagram that they wrote and realize that they did it wrong. But I mean, that's the kind of thing that like having the knowledge of why the thing is wired the way it does can save yourself hours of time. And so, I mean, that's the point where having the broader knowledge of why you're doing what you're doing becomes relevant.
All right, I'm mindful of time and I want to answer I'd like to discuss the final audience question, but hopefully we've got time for one more after that. So this was specifically about let's see, many of the comments in the first and second sessions note that the need to build bridges across disciplines. So as a panel, what are your thoughts on developing, I guess, quantum information science engineering minor, maybe rather than a modified BS program, Bachelor of Science? It seems that this would provide a better avenue for mixing up different disciplines.
Well, you can easily take the courses from, if you have the preparation for them, you can easily take the available quantum information courses. I think at any university, you don't have to be in a department. A minor could be organized. We don't have one currently. The students who've been involved, we have a very robust IQWISE, Interdisciplinary Quantum Information Science and Engineering Student Group, which is the descendant of an IGERT program we had that I co-directed years ago. And they run seminars and they have outreach activities and other things, and have a robust seminar series currently on Zoom, which means we can get people from overseas without having to pay travel costs. And they have had some thinking. I know I talked with several of them. Well, it's a while ago because it was on my campus office, to which I have not been in a year, almost a year, about a certificate program. And there is a procedure to have a certificate program. Whether or not you need a formal certificate or a minor, it's just a credential. Right now, if you take the courses to provide that kind of background, it's on your resume when you look for a job. You will get a recommendation if you've done an internship from whoever the supervisor was there. And if you've done a thesis, a master's thesis in this field, you have done it there. And so the main thing for the universities to have is the right set of courses and making them accessible in the way that, say, a course in my department isn't requiring excessive prerequisites for people coming from other departments.
David, Blake, do either of you have thoughts on this?
Yeah, I mean, I think top of my mind is just, the realization, of course, that you learn by doing. And particularly in a discipline like this, just the need to develop experience in the actual, doing of these activities, as opposed to sitting in a classroom and hearing somebody talk about them. And it's a certain kind of knowledge that you obviously acquire from listening or reading, and in the modern era where you can access information and listen to lectures from all over the world. I think that the real value is that opportunity to learn by doing. But that brings with it a big challenge, because this field's also, it's technically demanding and therefore very expensive. And not every university has a lab set up for educational purposes that contains a dilution fridge where you can learn by doing hands-on how to wire a fridge, or why you would wire it a certain way, and those aspects. So, I think there's an opportunity here for universities to come together and say, a single university is really going to struggle to provide a training program that's hands-on across the various different technical disciplines, but perhaps together they can each contribute some component of that, and actually allowing students to kind of move between that, having that hands-on experience. And it's really, and whether it's theory or experiment, I think it doesn't matter. I think equally, you learn by doing as a theorist, having to actually work through a problem on your own. I think it's about creating those types of opportunities and scenarios. But it's really challenging in this field as to how to do that, given the resources that are needed and the specialized equipment and labs and so on. And so I think we really need a fresh approach that's collaborative across, industry, academia as well.
Blake, do you have any thoughts on this? Or
I was kind of curious to ask you, Josh, a question to turn the tables a bit. What would you imagine are the sort of the minimum requirements to do, device theory or more of the theoretical disciplines in industry? Can you imagine a version of that which doesn't require a physics PhD?
yeah, so just for context for people, I spent almost 2 years working in industry in a quantum computing startup, the same one that Blake was at. And I was in the theoretical team. I was split across the algorithms team and the device physics team. And towards the end, I had a small team running, developing tools for verifying quantum computers. Yes, I think you can. We've just had our a quantum engineering minor approved at CU, and my thoughts are this. This is how I've decided to break it down, and I'm looking forward to seeing how other people are thinking about this. I have an introduction to quantum theory subject where the only knowledge we assume is students have taken linear algebra, and that's the only prerequisite, but we suggest they've taken some kind of calculus. And then we go through all of quantum mechanics, but without the emphasis that is usually given in physics courses. I don't care about solving the radial Schrodinger equation, which was like what Elliot said. We do talk about harmonic oscillators, entanglement, superposition. Then there's a second subject which focuses on device physics. So in that subject, we go through, assume that they've learned quantum theory, and then they go through ion traps, superconducting qubits, discrete variable optics, continuous variable optics, and even a little bit of like fermionic stuff. So we touch on a little bit on double dots and towards the end Majoranas. This has been reasonably successful so far. And then the third subject is a more traditional quantum computing, quantum algorithm subject. And this doesn't quite get you fully to the point where you can be a super productive member in a theory group, but I think it's the basis. And at that point, you can go and have on-the-job training from people in the device physics group or people trying to characterize the hardware or develop quantum algorithms. Anyway, that's my take.
Sorry.
Yeah. I don't know how are we going for time? I think we've got 2 minutes. So I might ask one more question for the panel, but let's try and keep the answers short. Many of the degrees that are being developed around the world and this country are actually being quantum technology programs built out of physics departments. And most of us have a very strong physics background and some engineering background. What advice would you give to physicists or people developing those programs to help integrate them either into industry or into more engineering mindsets, which are sort of crucial for developing scalable technologies? Jeff, you're first on my screen, so why don't we start with you?
Well, I have no degrees in physics, so I'm not sure I qualify to state this. Years ago, I believed, and maybe it's still true, that the only professional degree in physics is the PhD, whereas the bachelor's degree in engineering is a professional degree. If we're looking for this large workforce of bachelor's and master's people, you have to convince people applying and going through physics undergraduate programs that that's a good stopping point in terms of launching a career that validates them. I don't know how to do that. My friends who went to physics went through PhDs.
I think the biggest gap I've seen in physicists trying to make the transition to industry is comfort with the rudiments of software engineering, and particularly like how software engineers work in terms of testing and deploying code.
So sort of practical things, code quality, maintenance, and testing, rather than knowing any particular quantum assembly language or something like that.
Maybe not specific languages, but just like ways that you structure code, right? Like physicists end up often being very comfortable writing scripts, and then software engineers take one look at it and are immediately horrified. But with just a little bit of one semester of work, I think you could get to a place where they would already be able to talk much more productively. Okay,
David, do you want to finish off?
Yeah, I mean, I think it's again, that cultural aspect over the course of a physics degree and particularly into a PhD, there is this unspoken force that I think people feel that the goal is to be working on something new and rich and deep and fundamental. And if you're not doing that, then you're not doing good physics. And there's a pressure there, to ignore the practical, to ignore the technical. That's for engineering. The real physicist is going to be asking these much deeper questions. And that I mean, you emerge from a physics degree with that mindset, and then become totally useless in the practical challenges that we face in quantum technology at the moment. So somehow I think it's not just an exposure, but a development of what your mindset is towards using physics knowledge to solve what may be considered otherwise, dirty engineering problems that would be beneath the physicist. And that's it's a big cultural divide. It's not just in academia, and I think worldwide the whole structure of physics and journals and publications and prestige is sort of wrapped up in these, and Nobel Prizes is wrapped up in these ideas. But I think a program that recognizes that from the beginning and tries to kind of dislodge that type of thinking would be extremely powerful.
I totally agree. And people are mentioning ABET in the comments, and I'd love to discuss that more, but I think we should close the session. So I'm going to hand over. So first of all, thanks, Blake. Thanks, Jeff. Thanks, David. Really appreciate all your knowledge and insights on this. And I'm going to turn over to Lincoln, and thanks for everyone attending too for all the great questions.
Thanks.
That was an awesome session. In some of the responses to the audience questions, I suggested bringing these things back up again in session 5, which will get back to really what Jeff presented. What is the actual program for making a quantum engineering track or minor or undergraduate degree or whatever we're going to recommend for different university environments. So thanks a lot for that, Jeff. And I just wanted to mention that it is a separate, I got many questions about this, so hopefully you saw it in the chat, but it is a separate link for each session. I have sent out a link in the chat to an attendee only schedule that has the links for your convenience, because they can be hard to sort out through all of your emails. I think I had about 30 or 40 sort of frantic emails for people trying to find them. So hopefully that's helpful. Please keep putting comments in the Google Doc, and we'll have a little break now here and reconvene in about 15 minutes. Thanks.